It's new year, new me, sort of. Say I got a ponytail. That looks nice, right? All right. Anyway, so I'm sure you've seen this limit before in Calculus 1 specifically. I'm sure your professor just give you this formula, but never explained to you why this function, the limit of this function equals 1 as theta approaches 0. One way you can actually show this is you can actually apply L'Hopital's rule. So what that says is if you were to plug data into the function sine theta and theta, and if you end up with values of the form 0 over 0 or infinity over infinity, negative infinity over negative infinity, whichever that indeterminate form, then you can actually take the derivative of the top and the bottom and then plug in the same value again, and you can keep trying such that the denominator does not have 0 or infinity below. So if we were to apply L'Hopital's rule into this, we have sine theta, this derivative of that. Well, first sine theta, sine of 0 is 0, and then theta is 0. So you apply L'Hopital's rule. So we could take the derivative of top and bottom cosine theta, and then 1 plug in cosine 0. So that's 1 over 1. So it comes down to this. Pretty simple, but this video is going to be a little bit different. Instead, for today's video, I'm actually going to prove to you that this function, the limit as theta approaches 0 of sine theta over theta is equal to 1 without using L'Hopital's rule. And this is actually how the proof came to be with this. So let's actually first start off by sketching the unit circle, and we'll only and because theta is approaching 0, we're only going to be considering the first quadrant, so all positive numbers really. So I'm gonna draw the unit circle from the first quadrant. So what we have is this right here. It's our unit circle. This is 1, and then this is 1, 2, and then I'm gonna switch with different color markers to better interpret this picture. So, and then we have that the radius here is, we're gonna call this, it's r, so that means the radius here is 1. I'm gonna write r is equal to 1, and then I already wrote the 1. I don't know why I did that again. Great start, am I right? Here, and then this is theta. Okay, so we have this. So let's actually first interpret at this point here. So what I'm gonna do is I'm actually going to draw a line here. I'm gonna use green for this. So I'm just gonna draw the green line here. So I know it's not straight, but just that. So we're trying to find what this length is, and we know we have our radius 1, aka what is known as the hypotenuse, and theta. So think about this. When we're trying to find this length, we have our we're trying to find this length, but we're also given our hypotenuse. So what is this? Well, if you remember back from your days in high school, we have our trig functions. This is considered the opposite, and then this is the hypotenuse. So what does that give? Opposite over hypotenuse, and obviously ours, the hypotenuse is 1. So what does that equal? So that means this is this is sine theta. So this green marked length right here, this is sine theta right here. Sine theta. Okay. And then we we need to consider this length here. So recall that the arc length is actually, I'm gonna write this arc length. This is equal to your radius. The radius is 1, and then multiplied by your theta. So this would mean radius is 1 times theta. So that means this length right here is theta. Since this thing is marked in blue, I'm actually just gonna write theta right here as blue. Right here. Okay. And now I'm gonna use a different color marker for this. I don't know why I keep saying pen. This is a whiteboard. So let's use purple for this one. And I just dropped my marker. All right. So let's draw the line here. Extend this up. And then we're actually going to extend this line over here. So I'm just gonna mark some dots here, dot, dot, dot. Now, we don't know what this length is exactly. However, what we are given is that this length from here to here is 1, and then we're also trying to find this length. So again, same thing as like previous before, we have our opposite and adjacent. So opposite over adjacent, this would have to mean that this purple length is equal to tangent theta. So I'll write tangent theta right here. Okay, so now that we have these 3 lengths here, we have our sine theta, theta, and tangent theta. Let's actually compare these three lengths. So let's write here. I'm gonna use a black for this one. I have like 8 markers, so I got a lot of variety on me. So let's write our inequality. Sine theta is, and because this is approaching 0, it's positive, so we can actually include the equal sign. Sine theta is less than theta, and then less than tangent theta. And again, what we want to achieve is, so let's assume we're looking at the positive number. So we want to find the limit as theta approaches 0 plus of the function sine theta is sine theta over theta. So this is what we're trying to show. So this might, come to a halt when you're trying to think about what do we do now? So why don't we instead actually take the reciprocal of this entire inequality? So take the reciprocal, we have 1 over sine theta. And don't forget, because we're also flipping the reciprocal, we're changing the signs here. So this is 1 over theta, and then so recall that tangent theta is equal to sine theta over cosine, sine over cosine. So let me write this, equals sine theta cosine. So if we were to flip the reciprocal, so that will be 1 over tangent theta. Also rewritten as we can say 1 over sine theta divided by cosine theta. So in other words, it's the same thing as rewriting it as cosine theta over sine theta. So that's what we have, cosine theta over sine theta. So now the rest is simple from here. Now let's actually multiply let's multiply sine to this entire inequality here. I'm gonna draw an arrow. Do I have room for this? Yes, okay. I'm actually gonna put this right here. So we multiply sine, so this would mean we have 1 is this, and then, oh, we're getting closer. We have what we want to achieve. Greater than or equal to sine theta, then greater than or equal to sine times cosine divided by sine. The signs will cancel out, so we're left with cosine theta. And now all that's left is, let's take the limit of each of these functions. So I'm gonna write this out. The limit as theta approaches 0 from 0 plus 1 greater than the limit as theta approaches 0 plus of sine theta over theta is then the limit as theta approaches 0 plus of cosine theta. So this is straightforward. There's no theta to plug in it into here, so this would mean this is just equal to 1. So we have it's 1, and then we don't know what this is, so that's what we want to show. So we can actually just write this as the same, keep it as it is. 0 theta plus sine theta divided by theta. And then if we were to plug 0 plus, it's a very, very small positive number that's getting really, really close to 0. So plug in 0 plus into cosine theta, you actually get 1. And so this is where it gets interesting. So we have that 1 is greater than or equal to the limit as data approaches 0 plus assigned data over data greater than or equal to 1. So what does this mean? Well, we can by actually using the squeeze theorem, we can actually conclude that the limit as data approaches 0 plus of signed data over data is equal to 1. Squeeze theorem says that you have two functions. We'll call them f of x, g of x, and h of x. And we'll call the limit, we'll call the finite number L. So squeeze theorem says that if you have those three functions, and then if you have the limit as x approaches a, we'll call it a, excuse me, as x approaches a of, what's it, f of x, that's equal to L, and then the same thing but h of x, that's also equal to L. So we can, squeeze theorem says that g, the limit as x approaches a of g of x has to also equal L, which is the same thing as what we're using, the squeeze theorem right here. So we have one side, we showed one side, so now we have to show the other side, the negative, the 0 negative. Well, similar argument shows, but we're actually gonna take a little shortcut from this. There's still my blue fell on the floor. So we need to show the limit data of 0 from the left, this time the left, of sine data over data is also equal to 1. How do we do that? Well, here's a shortcut what we can do. So let's say we plug sine data of 0 minus and then 0 minus. So what that says is, because 0 minus is a very very small negative number as it approaches 0. So sine is an odd function. So what we can do is we can actually take the negative. So sine, and then 0 minus is the same thing as saying negative 0 plus. So instead we're going to write the 0 plus in replacement, and then divide it by, say the same thing as before, 0 plus. So the negatives will cancel out. So that means we have sine 0 plus over 0 plus. And we have shown that the limit as data approaches 0 plus from sine data over data is equal to 1. So we can say, as we take the limit of that, that means this is also equal to 1. So we have shown that the limit data 0 plus sine data over data is equal to 1. The limit as data approaches 0 from the left as sine data over data is equal to 1. Therefore, we can conclude that the limit as data approaches 0, coming from both sides, of sine data over data is in fact equal to 1, like so. No L'Hopital's rule. This is how it all starts. And I already did the calculations and already compute using L'Hopital's rule showing from earlier. So it works out the same as so. So that's all I have. Thank you guys for watching. I also did the computing the improper integral, so you should definitely check that out. Also have a playlist of math videos that you should also check out as well. And you're gonna see more of my hair tied up in future videos, so stay tuned for that. I have really long hair. New year, new me, as they say.